Okay, so these problems are to add on to the examples I gave you for section 7.1, which was the class meeting right before we took the chapter 6 test. I think I left off with number 9, so beginning with number 10. I actually completed number 9 in class. So in number 10, you're being asked to do the inverse tangent of negative 4.1. You are allowed to use your calculator and round to 2 decimal places. Remember that everything you're looking for in here is an angle, but you're finding them in restricted areas because inverses are only defined in restricted areas. So this is the restriction for the inverse tan function. And you're looking for the angle that's associated with this. I mean, you're actually going to put it into the calculator just like this. I mean, if you did want to rewrite it the way we did, not that you have to when you're putting it in the calculator, you can rewrite and go from an inverse statement to a non-inverse statement just by switching these two. This is just so you're a little clearer on what you're actually looking for. You are looking for the angle such that the tan value is negative 4.1. It's just a little easier to understand what you're looking for when you're looking for an inverse. However, you will be putting it into the calculator just like this. Your calculator only gives you the reference angle, and then you just have to make sure that the reference angle that you're being given lies in the restricted zone. So when you put this into the calculator, you should be in radian mode. Just going to go second, inverse tan, put in the negative 4.1, and you get, rounding to the hundredths place, as the instruction said, negative 1.33. Which is perfect because, like I said, the calculator only gives you the reference angle, but this is perfect with respect to direction because the negative says that you're rotating negatively because you can't possibly be in this quadrant. You don't have tan values that are negative in quadrant 1. And remember, you only have these two quadrants as your options if you're going to be in the restricted zone. So you have to be down here anyway. And yes, your reference angle is 1.33. But if you're trying to tell somebody where you rotated and in what direction you rotated so that you got here where the terminal side is, that would be theta and then the full negative in front of it. So actually what the calculator gave you is perfect. That is not always the case. Sometimes you have to work with it, the reference angle given by the calculator to get in the restricted zone. Okay, and problem number 11, we're moving to composite functions. You have inverse on the outside, non-inverse statement in the inside. So if you look to the theorems and definitions that I gave you for these composite functions, please find the theorems and definitions that were given for inverse on the outside, non-inverse on the inside for cosine. And you'll note that for those problems, the x value has to be in between 0 and pi. Now, if this x value, this is the x value they're talking about, if it is between 0 and pi, you literally have no work to do because in that case, as the definition that you're seeing on that page says that if this is the case, these cancel and the answer is just simply equal to this angle. So you want to check that out first. Put the angle that they've given you here and then just ask yourself if that's less than pi. You're probably going to want to think about 1 pi in terms of ninths so that you can make a comparison. 1 pi that you see right here is the same thing as 9 ninths. 7 ninths is less than 9 ninths. So, and these are little equal signs, excuse me. This is less than or equal to 9 ninths. So because it falls in the restricted zone, this cancels this, and your answer is the angle 7 pi over 9. Okay, it's when this angle doesn't fall in the restricted zone that you have quite a bit more work, as is the case in numbers 12 and 13. Now, I may have done 12 for you, but I don't know without looking at the video. So, because I skip around, sometimes I'll just do it again. Okay, so inverse sine on the outside. So look for the composite functions, and specifically the definition for composite functions on sine, where inverse is on the outside. For those problems, the composite definition, it says that x has to be in between negative pi over 2 and pi over 2. Okay, so let's check that out. Remember, this is the x value. You want to check out that starting value. Okay, they're talking ace. I want to compare that. I mean, since it's a positive, I'm comparing it to the positive value rather than the negative one. I can turn that into eighths very easily by multiplying the top and the bottom by 4. That would give me 4/8 instead of 1/2. Those are equivalent. However, in this case, you see that the value they've given you is not less than 4 pi over 8. So we're going to rewrite this problem. You can only rewrite the problems when the non-inverse statement is on the inside, not when it's the inverse. When the inverse is on the inside, the value that they give you will either be defined or undefined. So what we're going to do is, first of all, let's try and see the details of where the original angle is. If we were to go to 9 pi over 8, because we're going to try and mimic all the original details of this problem in conjunction with the restrictions for inverse sine. So originally we're supposed to go to 9 pi over 8. This would be the 1 pi mark, which is the same thing as 8/8. Therefore, the reference angle is 1 pi over 8. Values when you're doing trig can't be equal unless the reference angles are equal. So number 1, you want your reference angle. When you redraw this picture, your reference angle should also be pi over 8. Number 2, I want you to note what sign does this trig function have when you're in quadrant 3. If you remember the saying, all students take calculus, which I use quite often, down in this quadrant, all students take. Take is for tangent and cotangent being positive, therefore sine is negative in this quadrant, where this rotating arm is right here. Sine is negative. So you want your sine to be negative when you redraw this picture. Furthermore, you need to obey the restrictions for the inverse sine in this problem. And that would be, I'll just do a picture for that same statement that I did up there, that you can be anywhere between pi over 2 and negative pi over 2. So this picture basically says the same thing as this. So when you're drawing your picture, if you are going to stay in quad 1 or 2, and you want a reference angle of pi over 8, and you want your sine to be negative, and you know that you have to stay in here, you need to be down here. This is where your terminal side is. So you want to say that the reference angle is pi over 8. That's just your reference angle. But when giving your final answer, you want to say, how did you get here to this, where this terminal side is, without rotating through quadrants 2 or 3? And that would mean you would have to rotate negatively until you rotated through an angle of pi over 8. So your final answer here is theta equal to negative pi over 8, because by giving that answer, you've obeyed the restricted area. You're in one of the possible places you can be for inverse sine. You have the same reference angle, and you're in a place where the sine value is negative, as it was in the original rotation. Okay, so this is your final answer. Likewise, in number 13, let's take a look at that and see whether it's a bunch of steps like this last one that I just did, but I believe it is. So for number 13, let's see, what problem do we have? We have inverse tan of 6 pi. Again, only try this rewriting and trying to satisfy the specifications of the original angle when the non-inverse function is on the inside, not when the inverse is in here, as will be the case in 14 and 15. Okay, so the restrictions for inverse tan when you're doing a problem like that is that this x value needs to be in between negative pi over 2, non-inclusive of the endpoints, and pi over 2. Okay, it has to be between there and there. So let's see if this value that they're giving us is, because if it is, we hardly have any work. These will just cancel. Okay, so 6 pi over 7 compared to pi over 2. A little bit hard to compare these two because they're not the same denominator. So if you want to just quickly turn them in both into 14 by multiplying this by 7 and over 7, you'll have this pi over 2 represented as 7/14, so it's the same as 1/2. And I can multiply this by 2, top and bottom, and then you'll have 12 pi over 14. Is this less than this? No. So since this angle does not obey that restriction, you're going to try and check out all the details that have to do with going to 6 pi over 7. So if you went to 6/7, you'd be right here because this is 7/7, 1 pi. And you're only going to 6/7. So in that situation, you want to look at the reference angle because you're going to mimic that in your redrawn picture. So this will be reference angle of pi over 7. We want to make sure that when we give our answer we have a reference angle of pi over 7. Excuse me, let me rewrite that. That's one thing we want to go for. Then also let's look at what sign does the tan value have when you're in quadrant 2. Again, using all students take calculus. Students, the word students being here. Students starting with an S means that sine and cosecant are positive, therefore tan is negative in this quadrant. So we want to be in a quadrant where the tan is negative, and then third, we want to obey the restrictions of inverse tan, which is that I'll just do a picture of this now. I already wrote it like this, but we can be anywhere between here and here. Anywhere between pi over 2 and negative pi over 2. Okay, so if we did that, we want the tan to be negative. Nothing is negative here as far as the trig values go, so we have to be down here. We want our reference angle to be pi over 7, but then our final answer is, how did we get the rotating arm called the terminal side, which has to do with theta, how did we get it here without spinning through these areas, quadrants 2 and 3, because you're only allowed to travel through quadrants 1 and 4. So that means we had to rotate negatively, and then the pi over 7 is how far we had to rotate. So final answer, negative pi over 7. Very similar to problem number 12. Okay, moving on to 14. In problem 14, this is also a composite problem. Let me copy that problem real quick. That is regular cosine on the outside, inverse on the inside. So look up the restrictions on your theorem sheet, and it says that when cosine's on the outside and inverse cosine on the inside, that this x value needs to be between 0 and 1. And again, as I've mentioned in the last few problems, if this value is where it needs to be as far as the restriction, you have no work to do, as the theorems say, that this, whatever this x value is, if it's in the restricted zone, these would cancel, just leaving you with the x value. And it is, because this is 2/5. Is that less than 5/5? Yes, it is. And therefore this cancels with this. Final answer, 2/5. Okay, last problem. Let's see. Okay, so last problem is cosine on the outside, inverse on the inside. I had mentioned in the last few problems that all that redrawing so that you could go on with the evaluation of the composite function can only be done when the non-inverse function is on the inside, inverse on the outside, which would not apply to problems 14 and 15. So this one is 1.9. Again, you're using the same restrictions in 15 and 14 because both of them have non-inverse on the outside, inverse on the inside. So again, the x value they give you, which is this 1.9, has to be between 0 and 1. It is not. 1.9 is not less than 1. You cannot rewrite this, and you can even put this in your calculator. You'll see that when you do second inverse cosine 1.9, it shuts down because this is an undefined value with respect to the inverse function. So this is just undefined. Okay, that completes section 7.1. Just wanted to do the rest of the problems for you. Let's see if I can turn this video off now. That should be good.